I've given you all the background that you need to understand a normal distribution. We've talked about how it is we create data. We've talked about how we can look at that data by creating measures of central tendency, variability. And now we need to put those two concepts together with our idea of a normal distribution. Because the normal distribution is the important thing in statistics. We're going to build a lot off of this normal distribution. The curve itself is actually an equation. So there is a mathematical equation that will produce a normal curve. I'd show it to you, but it'd be scary. Because there's a natural log in there, and there's a couple like things that don't look like math in it, kind of words in the middle of an equation. So I'm not going to show it to you, because you never ever have to sit down and write out the equation to draw a normal curve. This is not calculus, right? Calculus is where high school math lost me. I'm like, I'm done. I don't get it. So we just have to sort of accept the beauty of the normal curve, and we're going to rely on the works of others that have gone through and created our awesome little chart here for us. Okay. So the normal curve itself is a mathematical construct. Up in my office, I got like this $80 book that's all about constructing different shapes of distributions. There's the Weibull, there's the chi-squared, there's the negative binomial, there's the Poisson. There's just a whole list. If you want to draw a curve, you come up with an equation, and the curve will have that shape, and you decide what parameters, like mean or variability, will shape that curve. So this is our normal distribution. We've talked about it before. We're just going to add a couple of caveats to it. Okay? So for us, we have to remember that mathematically there's this concept of infinity. And the tails of our distribution theoretically can continue on to infinity without ever actually crashing and touching the x-axis. It's a small little detail. In terms of the shape of a normal distribution, it'll always be unimodal. So there'll always be one hump. It is always symmetric. What does it mean to be symmetrical? This is first grade, by the way. Abby learned this last year. What does it mean to be symmetrical? It's the same on both sides. So you can take a shape and draw a line through it, and if you were able to fold it, it would perfectly match. I missed it. That's pretty close. Right? The line straight down through the middle, we fold it in half. It is perfectly symmetrical. Which is also the reason women wear makeup, by the way. Should not be a secret. All right. Last but not least, it is bell-shaped. Again, one mode. You'll hear that that term used, the normal curve, as the bell curve. The mean of our normal distribution is our theoretical population mean. So that's mu. And mu is the average if we could measure it completely. So the example I'm going to use today is shoe size. We all have shoes on, I hope. I did see one guy walking on campus the other day without shoes. I was like, weirdo. All right. What? What the hell does that mean? What about, I was going to say, what about the dining hall in Sino? It sounds like a made-up thing. But anyways, take a picture of a sign the next time you see, like, barefoot friendly. leave Travis alone. He's a busy man.
My high school was a barefoot high school. And it was
Okay, I'm done. This is silly. I'm done. Time out. Back to me. My class. All right, so shoe size. I'm looking around. We all better have some form of shoes covering our feet. Okay? Theoretically, we could find out what the average shoe size is in the world. We would ask we don't have to ask, we can just measure every foot. You got to measure both the left and the right, because some people have different size feet. You could do that, right? It would take forever. It would be really expensive. But we could find out what the population mean for foot size is. Would anybody want that data? Shoe companies. Why would a shoe company want that data?
Can't they just look at their sales?
They could look at their sales. Like maybe people who have size 8 shoes buy more shoes because more shoes are available than if you have size like 11 feet. Because there's not a lot in 11, particularly in 11 wide. I end up with going in the store and show me your one brown shoe in 11 wide. Okay. So if we think about this normal distribution, if we're, for example, a shoe manufacturer, like, I don't know, Nike, we have to decide how many shoes we should make of each size. Should we make an equal number of shoes that are size 10 as we make size 25? Why not?
One person.
Why are you discriminating against people with big feet?
I mean, there's like one of them.
Yeah, his name is Shaquille O'Neal, right? He has like a size 25 or 32 or something ridiculously huge, like size of your head shoe. Nike doesn't need to just make sure that there is a new Air Shack in every Foot Locker of size 25, because nobody will buy them. And what will happen to Nike in those shoes? They're going to lose money. They're going to lose money on those shoes. So if you're Nike, you want to know, have an idea about the distribution of foot size out there. Having a normal distribution, because again, normal distribution we find in nature all over the place. If you're Nike, somewhere in your shop, you've got one of these when you're figuring out shoe size and how many shoes to make of each size. We also want to know the standard deviation. We want to know how much variation in shoe size there is. Because remember, the mean gives us the center, but it's the standard deviation that gives us a better idea of the volume for those shoe sizes. In a normal distribution, both of these numbers are important. Like I said, if I were to show you the equation to draw a normal curve, about the only thing in it that you would recognize is where mu is and where sigma is. Okay. So you would see how it affects the shape of the curve. Okay. Because the field of statistics and researchers in many fields have found that through the empirical rule and through what we're about to do today, normal distribution is a fairly good predictor of distributions in nature. So when you think of things like sizing, the normal curve is actually really good for sizing. I mean, sizing for clothes, for shoes, hat size, condom size, what else? If you're manufacturing a product, you want to know which sizes to make it in and therefore reduce waste, but also make the sizes that people want to buy. It turns out lots of attributes are normally distributed in the population, and because of this, we can use the normal distribution for inferential statistics. That's what we're doing here in this class. We're making inferences. We are taking data that we have, our sample, analyzing it based upon our theories of the population and how the population should be shaped, and making decisions based upon those distributions and those results. If that makes more sense to you than it does to me right now. So next week and the week after, when we start talking about testing hypotheses, it's because we're here's a great word for it. We're placing faith in this normal distribution. Our repeated experiences of finding the normal distribution allow us to make inferences and use it to test hypotheses. So here's an example of in the world. IQ is how we say we measure intelligence. But that's not entirely true. IQ is a standardized test. So what we have done as statisticians and researchers is forced the raw score that you take on an IQ exam to fit a distribution that we believe exists in nature. So if you look at something like the bell curve, there's a book called The Bell Curve, which was about intelligence and sources of intelligence, and it was written by Charles Murray in the mid-'80s, slightly racist, but what Murray sort of lost was the idea that we have constructed this bell curve, we have constructed the distribution, and then standardized the test scores. Has anybody taken an IQ test? You take the long one or the short one? Yeah, well, that's fine. Well, what we have done is we have artificially said that the average IQ score in the population should be 100. And how did we do that? We made 100 the mean of the normal distribution for IQ. We've said it'll be 100. And what does it look like we've made the standard deviation? Right? It's about 15, right? Plus or minus 1 standard deviation, so it's about 15. Okay. And then when you take the raw scores, we convert them into IQ scores. And this is what we do for SAT, ACT, LSAT, virtually every test that you take where you're using it to compare yourself to somebody else, it's because we've standardized it. So I've introduced that word, standard. Mathematically, we have a distribution called the standard normal distribution. And the reason we've done this is because we want people to have, regardless of mean and standard deviation, one set of scores to work off of. So again, we don't want people to be confused, because if we're talking about shoe size, the average will be 8. If we're talking about IQ, the average will be 100. If we're talking about height, the average will be 5'10", whatever. So for us, when I say standard normal distribution, the standard normal distribution starts with a mean of 0 and a standard deviation of 1. We in statistics use this to create a method by which to compare different distributions at the same time. Let's see who came in late. These guys. Now, if you've taken probability and statistics in high school, you have heard of something called a z-score. A z-score is the method by which we can take different samples and compare them. So for me, I could take the sample from my Tuesday class on test scores, midterm scores, what's their mean and their standard deviation, and I can compare it to my Thursday class and their mean and their standard deviation. And so if you've got a friend in the Tuesday class and they come, well, I got this on Wood's exam, what'd you get? Well, I got this score. Well, we can compare where you are in the two classes. In order to do that, we've created a z-score. Let's see, I think it's the next slide. Let's look at a z-score. A z-score takes your raw score and places it relative to the mean So that's what the first step is. Real hard math here. You're going to take your score and you're going to see how far away it is from the mean by subtracting your raw score from the mean. Right? Real hard math. Subtraction. Really hard math. So if we think about our distribution again, first of all, what are we doing? What are we doing by subtracting a raw score from the mean? Yeah, I'm just seeing where on my curve here, how far away I am. So I am this far away. That tells me the distance. But we know that a standard curve, the distance from the mean isn't the important thing. What is the important thing? Think back to the empirical rule. Is it the distance from the mean that's the important thing? The important thing is the distance from the mean relative to what the standard deviation is. Because again, what does the standard deviation do for the shape of our curve? If I have a high standard deviation, what does that do to a nice normal curve? It flattens it, right? Because I have to go wider out further from the mean. Right? If I shrink the standard deviation, it makes it peaked. Remember that? So even though I know how far away from the mean I am, I still have to control for the fact that it's really the standard deviation that tells me how much of that distance in the totality of the curve that I am away from the mean. Let me show you. Okay. So here's one where I have the same mean, but the standard deviation varies. So I have two curves, one that's narrow, one that's wide. And if we look at the curve, at that spot, which curve have I taken up more of the space that's below my score, right? Because I'm a test score. I want to know how much higher I am than everybody else. Is it the narrow curve or the wide curve where I've taken up more of the curve space? It's the narrow one, right? Because what's left in the narrow curve? Well, what's left is just like that. But what's left in the wider curve? That plus all of this. Did that make anybody have a click? Okay, I got one person to click. Who right now is still totally confused? Anybody willing to admit it? Thank you. It does, because here's another little quirk about our curve. Maybe that's what I forgot to remind you guys of. So we have here with our standard normal curve, I've told you about the shape of it. You're right, Hampton, my fault. I forgot to explain one very important thing. All of these curves, they have one thing that's the same in each of them. And that's that the area under the curve, no matter what its mean and no matter what its standard deviation, is always 1. That's a constant. So going back to like high school geometry, where you had to do the area of different shapes. Like what's the area of a square? Length times width, or if it's, or length squared, or width squared, or one of the sides squared. That's why it's called a square. Fun fact. All right. What's the area of a triangle? Half of base times height. Why? Because a triangle is half of a square. Okay. Well, what's the area of the curve? 1. That's great. You don't have to like remember what you're multiplying. It's not like what's the area of a circle. Anybody remember the area of a circle?
Circumference squared.
Pi r squared. Sure, I don't know. I'm guessing that's right. So no matter what the shape was, there was always some very unique equation to that exact shape. Oh my God, the shape of a rhombus. Well, no, a rhombus is just a square with 2 triangles, right? So, yeah, aha. And so a rhombus, you had like A and B and then C and D, and you had to, yeah, none of that. None of that. What's the area of a normal curve? 1. Always 1. It's a constant for us. The area of the curve, always 1. And we're going to do something with the area of that curve. We can also treat that area of the curve as a percentage. Because if the area is 1, wow, move a couple decimal points and you got a percentage. Awesome. There's one other mathematical concept that 1 is important to, and that's probability theory. With probability theory, no matter what the game or the trial, the outcome is always out of 1. So if you flip a coin, what is the probability that the coin is heads? It's 1 out of 2. One outcome out of 2 possible outcomes. Tails, 1 out of 2, 50%. That's it. Heads or tails. And don't tell me if it lands on its side. I don't want to hear that. You just nudge the table and it'll land on heads or tails. Don't be that guy. Okay? So if I use cards as an example, we're going to use 52 cards. We're not going to use 54 because the deck comes with 2 jokers. I never understood in poker why 3 of a kind beat 2 pair. I'm thinking 2 pair, that's 4 cards. That's a lot better than just having 3 cards that are the same. Well, it turns out, because mathematically, it is harder to get 3 cards that are the same when you have 5 in your hand than it is to get 2 different pairs in your hand. How do I know that? Because I had a sadistic probabilities professor that made us calculate the odds of each poker hand. So I had to prove why 3 of a kind was better than 2 pair. Because it's all about probability theory. All right. So this is going to be great for us because since we have a lot in math that is based around either 1 or 100, we can use them interchangeably. We can use this normal curve that has area of 1, probability of 100, and 100% and a probability of up to 1 interchangeably. And that's going to be great because that's going to simplify what we do with the normal curve. How are we going to do this? Well, we're going to use this z-score. Now let's look at the z-scores for a second. This z-score here, a z-score of 0, occurs when the mean and the x are the same in our equation. So when x minus mu is 0 is whatever number minus the mean, in this case 0 minus 0, to give us a 0, we're at the center. This is symmetric. How much of the area under the curve has a positive z-score? Half. How much of the area under the curve has a negative z-score? Half. Now the next step. A z-score is really a unit of standard deviation. We're going to go through some examples just to prove this, but for a z-score of 1, that is 1 standard deviation away from the mean. If you do the math real quick, all right, okay, that plus that divided by that, yep, 1 standard deviation away. 1 minus 0 divided by 1 standard deviation is 1, okay? So whatever this number is down here, that's going to be the distance away from the mean. Okay. Because it's symmetrical, that area is going to be the same as that area. Got that? I haven't told you what the area is yet. Doesn't matter. It's 1 z away from the mean. Okay. Of the whole standard curve is always 1. But when we start taking our curve and slicing it up in terms of standard deviation units, remember the empirical rule. Most of our curve, 68% of our curve, should be 1 unit away. And it's not like a linear transformation here, right? It's not like +1 standard deviation unit equals this much in the area of the curve. Because when we look at the curve, when we go from 0 to 1, that's a really big slice of the curve because it's taller here. But when you look from 2 to 3, that's a really small slice of the curve. There's not a lot of volume in there. There's not a lot of area that's in between 2 and 3. Why? Because it's curve shaped. It has a high center and low tails. Make sense? Yes, as a whole. If we go out from, and remember there's one other quirk here, right? And that's stupid infinity. Right? Way all the way out. Yep. Will you actually see people with shoe sizes of 117? No. You won't. So how much area of the curve is at 117? Well, it ain't 0 because we never actually hit that x-axis, right? But it is so small that you don't even can comprehend it as anything other than practically 0. Yes. We're using standard normal. But you can if you do what to it? Normalize it. If you convert it or standardize it, whichever way you want to do. So what we're doing right now is the question you're asking. That's what z-scores do. Let me go to an example. That's the easiest way for us to understand this. We have the SAT. And like I told you, the SAT is a standardized test. Let's say in the math section, the mean of the SAT is 500. How do I know that the mean of the SAT is 500? Well, A, because it's on the slide, but how do I know that? Who made it 500? The people who made the test, right? Remember, I told you this is a standardized thing. How do I also know that the standard deviation is 100? Because they made it that way. They said, this is the curve we want, okay? So, first question. What percentage of scores is less than 630? So I've got to take the 630 and convert that to a z-score. Okay? So how do I do that? What should I do? Let's bucket on the floor of this. We're going to take a question like this and break it down to its simplest steps. What's the first thing I should do? Like what? Of what? Like a pie graph or a bar chart? What kind of graph should I make? Yeah. First, the very first thing you all should do, right, is put the bucket of water on the floor by drawing the curve that we're going to be using. And that curve is a normal curve. Okay, it's got one hump. It's relatively symmetrical. I'm never actually any good at drawing, so it looks like a bell. We're ready to go. Let's put some color on our bell here. What else do we know about this bell? The means what? Okay. What else do we know? All right, standard deviation's 100. I'm not going to draw the standard deviation because that just tells me how squishy my bell should be. So I'm just going to skip that. Okay, what am I looking for? What about 630? Okay, so I know that 630 is more than 500, so I can put it on that side of the curve. What should I do now? Nope.
You take 630.
Nope. Look at the screen. What should I do now? I should draw a line or something. And what area am I looking for? So what should I do maybe? I could shade it. That's fine. I could draw a little arrow and say, go this way. No. Okay. We okay with this? This is bucket on the floor. I haven't actually done anything yet. All I've done is taken the information that they've given me and drawn a pretty picture. Why do I do this? Because I'm trying to simplify. I'm trying to take something that might be difficult and simplify it down. What have I done? I've taken words and turned them into a picture that I can now reference. If you can do this in math, this is one of the keys to understanding how to do complex problems. Simplify it, okay? So now what am I looking for? Well, I got to find the area under the curve. In order to do that, I calculate the z-score. Z. What is the value of z for my spot at 630? Now, Chase, what do I do?
All right. You take 630, subtract 504, then divide by 100. You'll get 1.3 for your z-score. And according to this...
Don't go there yet. Don't go there yet. Okay. So baby steps. We now have calculated what the z-score is for that spot on my curve. And that spot on my curve, I'm going to erase my z here, is 1.30. That's standardizing. So no matter what curve I have, with whatever mean and standard deviation I have, I've taken my scores and I've standardized it. Now, I can look on my z-table. So this is what I've given you. Bucket on the floor. What should I check first? Nope. Simplify, simplify, simplify. What should I check first? Well, what's the first thing I did when I had the problem? Drew a picture. What should I do here with my table? Look at the picture. There's a picture there. Okay? Why do I need to look at the picture? Why do I need to look at the picture? What am I trying to confirm?
That's the measurement for the amount that's behind. Well, that's lower than.
Less than my z-score. Okay. Listen, I can't explain why we do stupid stuff in the world, but one of the stupid things we do in the world is we actually have two different forms, actually three, different forms of z-score tables. I don't know which one's in your book. I don't care, because this is my training. My training is to always do less than z. Some strange German professor might teach all of his kids, make it greater than z. I don't care. We do less than z here. We always go backwards. So the first thing you need to do is make sure you got a chart that meets what you've been taught. I'm sorry. I always use this one. I'll explain that in a minute. Okay? So, are we clear in that? That's why we draw the picture. Why? So that we look at the table, we know we have the right direction. And believe me, there's nothing stupider than getting the right answer but doing the wrong process and really ending up with the wrong answer. Because you can mathematically do this correct, but when you write it out, you're like, oh, wrong direction. So, I've checked my picture. This picture looks just like the one I drew. I can't write on this, it's in Adobe. Okay, so I've got a Z number. What's my number again?
It is 1.3.
So here's how you use this. The first column has the first two digits of our z-score, 1.3. But then there's 10 numbers coming after that. The columns are for the number in the hundredth place. So 1.33, that's the tenths place. The next number after that is the hundredths place. And 1.30 is the first column. 1.3 down from 0, 0.9032. Now that my picture looks like the picture on there, what's the question? What percentage of scores is less than 630? What's the correct answer? 90%. Because a percent, you move the decimal over 2 spots. You got a real bad look, Aurora.
Yeah, I was really confused for a second, but we're good. I was really...
Because remember, area, probability, and percentage are all the same thing. They just look a little different when we actually say them as answers. Because that is 90% of the area.
I was thinking you were going with the entire area, and I was like...
Well, I know the entire area. What's the entire area under a curve? It's what? It's got to be less than 1. Because I only want the area that's less than 630. What's the area of the curve above 630? A little less than 10%. So that scores 631 all the way up to like 800. Does that make sense? I'm looking for heads nodding. I need the heads to nod or shake. Make sense? Okay. One more to sort of make this even more sense. I'm getting a new computer. You guys will never see it, so we'll suffer through this for the rest of the semester. This not working. Okay. The next question. What percentage of scores is between 450 and 630? Okay, what's the first thing I do? Beautiful. What's the next thing I do? Okay, what am I going to label it? Anybody? Okay. What else? Okay. What else do you think I should do? Okay, I'll draw lines. Oh, what? Huh?
Shade between,
Why?
because it says what percentage between those two.
Okay. All right, you're in charge now, Alex. Now what do I do? No. What do I do?
Now you just. Oh.
Write that down for me. Now you just do the math. Because that's the best. I will remember that for the rest of my life. So, Alex, what do we do next? Well, next you do the math. You ever heard the expression, no shit, Sherlock? My dad liked to use that one. Have you heard that one before? Okay. So, no shit, Sherlock, what do we do next? This being a math class and all, what sort of math should we do? What sort of math should we do, Sherlock? We got to do what? Somebody help Alex out here, because I got him laughing. Explain to me what we need to do. All right, why do we need to find the z-score for each of the numbers? Because that's how we determine what?
The percentage that is between
The area under the curve. Okay. What's the z-score for 630?
1.3.
Yeah. I'm not going to pretend we didn't already do that. What's the z-score for 450?
Negative 0.5.
450 minus 500 divided by 100 equals negative 50 divided by 100 equals negative 0.5. I like this example because it shows you how the z-score is really, again, a measure of distance from the mean using standard deviation units. In fact, I want you to write that down in your notebooks. A z-score is a measure of the distance from the mean in standard deviation units. So 450 is how far away from the mean? Well, in score, it's 50 away from the mean. But that 50 is half of a standard deviation, because in this example, a standard deviation is 100. Ah, some bitch. It's really that simple. It's really that simple, guys, because that's all the equation is doing. How far away are you from the mean? And then dividing it by the standard deviation units. No, we're not there yet. Okay. So we know that from 630 back is 0.9032. We got that, right? Okay. Let me do some erasing here. What do we do next? Okay, so now I need a z-score of negative 0.5. How do I do that? You flip your sheet over. Because I'm nice, I gave you the negative numbers. Okay, so a negative 0.50 is what on the z-table? Is what, Aurora? Okay. I agree. You're welcome. What next?
Subtract 0.3.
Why?
Because you're looking for what's between those two, and 3085 is the tail after.
Right. So if I wish I did this in different colors. Let's see if I can manage that without cursing too much. Okay. Here's my colors. So the first one that we found was 1.3, and that was all of this area back. The second number we found was for negative 0.5, and that was for this area. So in order to find the area under the curve that is still blue and has not been turned purple, we have to subtract the amount of purple that we added to the curve. Yeah? I really need to see heads nodding, because it makes total sense to me, but you guys, I don't know. Yeah? Okay. So we'll subtract it. And somebody use their calculator, because I'm not going to make a fool of myself.
I already did. So 59.47.
All right. What percentage of scores is between 450 and 630?
59.47%.
59.5%. Okay. So this is great. We can take a distribution that we have, and we can use z-scores to standardize it. And because we've standardized it, and because there's people out there who know calculus way, way better than I do, we've gone out and we've just computed every point. Every point. All right, there's an applet. I've got a link for it in the Moodle page. I just want to go over sort of what we just did and show you that our mean was what? 500? It's too dark in here. I can't see my keys. My standard deviation was... Okay, now look, I typed in 500, and what did the applet automatically do? Set the mean at 500. And now I'm going to type in the word 100, and what's going to happen?
It's going to change standard distribution to 100.
Yeah, so I'm going to be, for 1 unit away, I'm going from 1 to 100. That 501 is going to turn into a 600. You're starting to get it. Okay. Now my X score. My X was 630. And it shaded the area of the curve that was less than. And it gave me this number here, 0.9032. Look at that. Wow. The internet caught up to the 1600s when we had this stuff. Remember I told you, there's that quirky German guy out there that's training his students backwards. And this is why, again, I need to teach you guys bucket on the floor. Because let's say you go to the website and you type the numbers in and it gives you this. And you're like, wait a minute here. The shading's on the wrong side. Again, we don't have a universal standard in math. We just don't. I don't know why we don't. So let's say somebody, like I said, crazy guy in Germany is teaching his students the other way. That's fine. You can do it that way too. Okay. And then our other number was what? 450? And there it goes, 30854. There's a lot of rounding. So there's rounding here to 4 significant figures. For the most part, my guideline is use what they give you. You notice that for z-scores, the table wants 2 digits. So if you're calculating z, you need to have 2 digits, because that's what will make your table work. Yep, we did it right. I don't know why I put that there. Okay, one more great thing about this. What we were dealing with in that last example was when we knew what the distributions mean and standard deviation were, because they were standardized in their creation. But what about if you don't know what the population parameters are? Back to my shoe size example. I'm Nike. Do I want to go out and measure the foot size of every person on the face of the earth? No. What could I do instead? Get a sample. Put an ad in the local paper. Show up to this place for $10. And we do this in social science all the time. You put an ad in the local paper or Craigslist. You know, call this number for a chance to earn $10 in 5 minutes. And then they call, and then they come to campus, and you're like, I'm going to measure your foot. You want your $10? And you measure their foot. Okay, so you get a sample, whatever. Nike employees, perhaps. Just don't actually measure the guys under contract that are basketball players. As long as you think your sample is random and diverse and a good sample, we can take a sample and we can still transform these into standardized scores. All I've done with the equation is just use the sample letters of x bar instead of mu and s instead of sigma. But it's the same exact equation. The reason we can do this, or we want to do this, is not only because we might not know what the population parameters are, but we might, again, have two separate samples, and we want to compare their area or volume. So imagine we want to compare, you're talking with your roommate, and you get your score on this midterm that's an 80, and you say, you know, I'm doing okay, I got an 80. And he's like, well, I took my anatomy test, and I got a 75. And you're like, oh, well, that's unfortunate, you know, better luck next time. And that's when he starts duding you. Like, dude, you have no idea how hard anatomy is. Like, a 75 is really good. And you're like, well, okay, but still, an 80 is better because it's higher. Like, it's clearly at least a B. It's like, dude, you don't understand. Well, we're missing a piece of information. What's the piece of information that we're missing? Yeah, we're missing that important test information. So you, in your statistics quiz, you got a 75. The standard deviation in the class was 2.5. But the average was 80. Or sorry, I always do that, right? So the average was 75. You got the 80. You do the z-score. You got a z-score of 2. That's pretty good, right? Being 2 standard deviations away. Because if I remember my empirical rule, like 95% of my sample is 2 standard deviations away. Well, like the 95th percentile. Yeah? That's pretty good. All right? Top 5%. But then I do the math for the anatomy quiz, and oh, man. They got a 75, but the average was 65, because anatomy's wicked hard. And you do the, oh, Jesus. His Z-score is 5. Empirical rule only goes up to like 3 standard deviation units. I wonder what a Z-score of 5 is. Oh, no. Oh, some ramen. I'm the dumb one. Crap. Well, let's take a look. So remember, somebody remember these numbers. 65 to 75. 65 to 75. Computer choked. It gave me a probability back of 1. You know why it did that? Because there were so many zeros before it actually could find a real number that it just is like, I'm done. I'm just going to round it up to 1. I did it the other way and I said, well, how much is in the tail? 0. There's nothing in the tail. Your roommate probably got the highest grade in the class. As the z-score increases, the further away from the mean you get, which when you draw your pretty little picture means there's not really that much area left. Right? When you get far away, you're out in those infinite tails. And how much area is there? Just enough not to actually hit the line. Because we've told you that standard normal distributions go from negative infinity to positive infinity, and it approaches but does not touch the x-axis. We're talking like molecules of height in that curve. Yeah, I bungled that the last class. I tried to talk about how we're not really changing anything. We're just, it's a linear or direct translation, and then I tried to do the Fahrenheit to Celsius and didn't go well because I'm the only one that lives near Canada and can remember that. So I'm just going to skip that part. But remember, by standardizing it, we're not changing the shape at all. We're not, because they all have the same shape. They all have the same bell shape to them. What we are doing is creating units that respect the variability in that shape. Because again, tall and skinny, shorter and wider. By standardizing using standard deviation, we're just basically saying, instead of having overlapping curves, what if we just all had the same curve? All the same shaped curves. Well, what we're going to allow to be different at the bottom is the numbers. Converting those x's into z's, let us use that table so we can better understand the area of the curve. How are we doing? Math wasn't hard today. Where it gets a little weird is the magical properties of this curve. Like, I still don't think I have you guys convinced that there's a lot of curves out there in nature. But remember the weight stack. Remember I showed you a picture of the weight stack? The curves do exist. All right? When you get large samples, you find curves. Like really large samples, you do find curves. We've done it, like I said, when you measure things of people. They are, I think shoe size is probably the easiest one to grasp, because some people have a hard time finding shoes and some people don't. Well, it's because they're not selling shoes to big flat-footed people like me. They want to sell it to normal-footed people. And that's why they give them a bigger selection. And I get the brown shoe. Got like 4 versions of the brown shoe. Shoe shopping with me is really easy. Yeah, I got wide feet. I can't do that because they say it's wide, but it might not actually be wide enough. All right. I took my 4-year-old shoe shopping with me. We walked in the store. I looked for the 4 boxes that had the little wide tag on it, and I looked at them like, "We're done, John." What? I haven't even started wrecking stuff yet. Like, time to go. I don't need those shoes. I already have that pair. It's really quick and easy. What are we going to do next? Well, next, we're going to make the turn. Because all I've done now is just really teach you a little bit of math, and a really easy math. Now we actually have to take the math and start thinking about how we're going to use it to test hypotheses. And so that's what we're going to do next. So next week, we'll have one more week with this. It's your sort of soft introduction. The following week is the midterm week. And that's like, again, 1 through 6. We've done really no heavy lifting here. I just want to make sure that we all have these very simple concepts like central tendency, variation, curves, under control. All right? Last thing I'll say is the videos, I don't know if anybody's looked at the auxiliary videos for sections 3 and 4, like the video you're supposed to watch instead of coming to class. Has anybody done that yet? Well, I can go check because I can do that. I see everything you do in Moodle, by the way. What I'm doing is I'm doing exercises because that's what I would be doing. So like the examples we do in class, I would be assigning you homeworks if this were a regular sort of in-person class, and then we would be going over the homeworks. So this is like me doing that, but online. When I do it, I say hit pause and do it for yourself. Like I'm sincere. I actually want you to hit pause and do one for yourself. Okay?